Good evening. Can you all hear me? Can someone confirm, please?
Yes, sir.
Okay, right. Thank you. Let me share my screen. Okay, can you see the first slide or the cover slide? Can you see the cover slide, first slide?
Yes, sir.
Okay, right. Thank you. Right. I think in the first day school, I have started the section on open channel flow, and I explained that under open channel flow, we will be focusing on steady flow in open channels, basically steady flow in open channels. But we will look at both uniform and non-uniform flow conditions. Okay, so it would be steady flow, but we will look at both uniform and non-uniform flow conditions along channels, okay, open channels. And I also explained the difference between an open channel and then a pipe flow, I think, right? Okay, so in open channel flow, you have a free surface. Pressure is not basically the main factor. Yeah, the flow is mainly due to gravity. So gravity actually makes the water to flow. In pipe flow, basically it's the pressure, no, the difference in pressures will make the water to flow along pipeline. So it's a closed conduit. If you take open channel, can you all please mute your mics? So in open channel, the free surface is open to the atmosphere, right? So that is the difference between the pipe flow and then the open channel flow. And I have started the section on uniform flow, and then derived certain expressions, etc., related to the uniform flow conditions. But I could not actually go through with the section on the most economical section for open channels. A discussion about the most economical section for open channels. So today I'm going to start that one and then move on to non-uniform flow in open channels. Okay, right. So steady flow in open channels, and then this is we are still in uniform flow, and there is something called the optimum shape or the economical cross section for a given flow. Now, if I ask you, if you are to design an open channel, what would be the most preferred cross section, considering its economic aspects? I mean, to reduce the construction cost, what would be your preference, simply based on the construction cost, economical one? What would be your preference when it comes to the sections? Now, if you are to design a section, there are different shapes of prismatic sections. There can be a triangular shape, there can be a rectangular shape, there can be a trapezoidal section, there can be a circular section. So out of these four, what would be your preference, simply based on the economic aspects, the construction cost in the sense that the material cost, let's say.
Trapezoidal.
Hmm?
Trapezoidal section.
Trapezoidal, is that so? Is it? Is it the most preferred section? Isn't that a circular section? Now, if you take even if you take this particular diagram, now you have a the shape trapezoidal section, and then take this circular section. Now, circular section basically will be similar. I mean, if you take the area, pretty much similar to the same area of the trapezoidal section. But if you take the lining, this lining, along the circumference, this would be the least, no, for the circular section uh, compared to any triangular or rectangular or trapezoidal section. This the circular shape will give you the least lining material or least circumferential length, okay, along the perimeter. So that means you are going to use less material. So circular section is the most economical in that sense. But what is the problem with a circular or semicircular section, cross section? What would be the problem with this circular section? It would basically give the least, the smallest perimeter. This is perimeter, smallest perimeter. What is the problem with these cross sections, circular type?
Slow stability
Huh?
and maintenance.
Yeah, yeah, I agree with that. In a sense,
Maintenance cost is
yeah. Before coming to the maintenance, I think
the
even the
maintenance is problem.
maintenance, of course, will be a problem. But even before that, the construction will be difficult, no? Now, if you are to construct a channel of circular section, it is going to be very difficult in the construction. Now, setting out will be very difficult. Okay, circular one. Okay, even if you take a road, setting out of a curve is difficult, no, rather than setting out a straight road. So even in this case, when you have a vertical, that curvature is in the vertical direction. In this case, the construction is going to be really difficult if it is going to be a circular section. Okay, circular section, curved section. Forget about circular one. Even if it is simply a curved one, it is going to be very difficult. So circular sections are not preferred. If it is a very small diameter, then of course you can construct it possibly in a yard and then bring it to the field and then lay it just like you are laying a pipe, okay, concrete tube pipe or anything like that, and then you can do the construction. But if it is going to be a very wide channel, then the construction is going to be very difficult. Now you're talking about meters, maybe 20-30 meters or even more when it comes to the width of the channel. So you can't, I wouldn't say you can't, but it is practically difficult to construct circular channels or channels with circular sections. So generally the rectangular sections or trapezoidal sections are preferred. Even the triangular one is going to be difficult because of the workmanship. If it is a triangular one, then because of the workmanship, poor workmanship, uh, it is going to be difficult in the construction, even the triangular one, right? So very difficult to construct. So generally the rectangular ones and basically uh, the trapezoidal ones are preferred. Okay, trapezoidal ones are preferred. Now we are going to look at the trapezoidal section here. So let me take a trapezoidal section like this. I'm going to draw a trapezoidal section. A trapezoidal section like this, which is having side slopes 1 to n. Okay, 1 to n, side slopes 1 to n, and a water depth capital D. I'm going to take a depth of water as D, and then the bottom width taken as capital B, right? So the slopes are 1 to n, the water depth is D, capital D, and then the bottom width is capital B. Now with this one, I can basically define a trapezoidal section with a water level of capital D. Now suppose that you want to have a maximum discharge, okay? Maximum discharge along this channel, okay, maximum discharge along this channel, and you are having a trapezoidal section. We don't know the slope, okay, Okay, we don't know the slope, this 1 to n, or the water depths basically. And what we want to have an economical section for this trapezoidal channel. Economical section for this trapezoidal channel. Now, to do that one, now since this is the free surface, we have to fix in a way the area. Now, the reason is you can keep on increasing the water level, okay, keep on increasing the water level, keeping the side slopes constant, and that would increase the cross-sectional area. And at the same time, you can keep the water depth the same and then maybe change the side slopes in order to change the area. So the area will be dependent on both D and this 1 to n, this side slope. The area, the flow area along this channel will be dependent on this water depth and this side slope. Right. So here what I'm going to do is I'm going to use Chase's formula, and I'm going to write the discharge along this channel by multiplying or taking the product between the flow area and then the Chase's, the velocity taken from the Chase's formula. Now we know that the Chase's formula gives the average velocity as C into m to the power of half, which is the square of the hydraulic radius, and then I to the power of half. I is, if it is the uniform flow, basically I is your bottom slope, right? So m to the power of half, I to the power of half. So we can now write the expression for m. We know hydraulic radius is given by area, the flow area divided by wetted perimeter. So let me substitute that one here. So if I substitute that one, I'm going to get A into C. C is the Chase's coefficient, and A divided by P is your M, hydraulic radius, to the power of half, I to the power of half, right? I to the power of half. Now we are considering a given section here, because I can't change it. If I change it, then the problem will become more complicated if I keep on changing A also. So we have to consider a given cross-sectional area. For a given cross-sectional area, I told you that the given cross-sectional area would become basically a function of the water depth and the side slope. Right. So based on this diagram, I can easily write the wetted perimeter. Wetted perimeter is a length. Wetted perimeter is a length. So if it is the channel, open channel, this trapezoidal channel, wetted perimeter is from here to here, here to here, and here to here. No? That is the wetted perimeter. So how do I get that value? Wetted perimeter using the quantities in the figure. So wetted perimeter capital P is, this is B, bottom depth is B. B into 2 times this slanting length, or this inclined length, okay, slope. So 2 times that slope. How do I get that slope? Since the water depth is D, this vertical height is D, and since the slope is 1 to n, this would become dn. So if it is D, then this would become dn. So the diagonal length, which represents the side slope, will be dn to the power of 2 plus d to the power of 2. So then you can take d out, you get square root of n squared plus 1, and then since there are 2 sides, you have to multiply it by 2. So the wetted perimeter is now b plus 2 into d square root of n squared plus 1. Now similarly, you can get the area of this trapezoidal section, you can easily get the area of a trapezoidal section. We know the equation. So how do we get it? So we have to add these two lengths, okay, these two lengths, and divide it by 2 and then multiply it by the normal length between the two legs. So it would be B plus this free surface length would be B plus 2nd, okay, 2nd, and you have to divide it by 2 and then multiply it by the height d. So here you have 2b plus 2nd, and when you divide it by 2, you get b plus nd. B plus nd multiplied by d would be bd plus nd squared. So this is the wetted perimeter, and A will give you the flow area. By rearranging this one, now I can get an expression for the B. Okay, B will be A divided by D minus ND. So I got B from this particular expression. I'll call this one equation number 1. I'll call this one equation number 2. I will call this one equation number 3. And from 3, you get this one equation number 4. Okay, right. And then similarly, since I have got the value of B, I can substitute 4 into 2 and then get an expression for P in terms of A and D. Now, if you look at P would be now in terms of A and D, and then of course you have N. So the three quantities or three variables which would change P would be A, D, and N. Okay, and earlier I told you that we will be looking at a given cross-section area. Okay, given area. So my variables would be D and N. So keeping A constant, cross-sectional area, flow area constant, the variables, the independent variables for the dependent variable P would be N and D. So that is the water depth and then the side slope. Right. Now, why did I want P? Earlier, I told you that if it is going to be the most economical or the optimum shape, P is the wetted perimeter, and you have to go for a lower value of the wetted perimeter because you can then bring down the material cost. Material cost can be brought down by reducing the P, and at the same time you can see that the maximum discharge can be attained by a lower P value. Okay, lower P value. So then that means if I first consider the dependency of P with respect to the water depth only, okay, assuming that N is a constant, dP by dt should be equal to 0, because if it is the minimum one, okay, if it is the minimum one, if it is the minimum value of P, then at the minimum value of P, dP by dt should be equal to 0. So let me now differentiate the equation. I'll call this one equation number 5. So let me differentiate equation number 5 with respect to D. So when I differentiate equation number 5 with respect to D, I get minus A divided by D squared, because 1 over D, when you differentiate, it would become minus 1 over D squared. And then this whole term is considered to be a constant in this case. And then D, when you differentiate D with respect to D, it would become 1. So now this whole term dP by dt for a minimum value of P should be equal to 0, right? So then let's equate and get an expression for A. So I got an expression for A in terms of D and N. Okay, D and N. So this one is taken at the minimum value of P with respect to the water depth. So accordingly, I can get do the substitution. Okay, do the substitution for B here, and then I got an expression for B as well. So what I did is I substituted A here. Okay, A here, because A is in D and N, and did the substitution here and got an expression for B. So your B will be something like 2D into square root of n squared plus 1 minus n. Okay, right? So this is very simple. You differentiated and then got the terms, the expressions for the terms or the variables according to your preference. Right. Now I'm going to go further down. I got this A. Okay. I have rewritten A here. Right. Here. And then if this is A, I'll call this one 6. Now, since A is with D and N, I did the rearrangement of the terms, got D into the left-hand side, and got the square root of all the terms so that I would get an expression for D now. It's same equation, 6 equation, same, but moved all these terms to the left hand side and then got the square root. Okay, got the square root. Now, since this is D now, using A and N, and I can also get P from previous one. P is this one, and I know B is this one. P is B plus 2 into D square root of N squared plus 1. I can substitute this B in P, okay, and then I can get the expression for P as well. Okay, so I got an expression for P. So here, this is the expression that you have got, and then do the substitution for P. Okay, do the substitution for P and bring this D here. Okay, right, D here. So I got another expression. I'll call this one 8. Now I got an expression for P only using A and N. Now I don't see any D terms here. I only have A and N. And again, still I do not know the side slope. I know the dependency of P with respect to D, and I still do not know the dependency of P with respect to N. And I want to see how the side slope would affect the minimum wetted perimeter. Okay, minimum wetted perimeter. So to do that one, I know that dP by dN should be equal to 0, no? Should be equal to 0. And even if you take the square of that one and then differentiate it, you would get the same thing. The reason is, if you differentiate dP squared by dN, this would be 2p into dP by dN. So no problem with that one. When you make it to 0, since P is not going to be a 0 quantity, then this one will have to be equal to 0 again, right? So I differentiated the square of the wetted perimeter with respect to the side slope now. So if you differentiate this one, you're going to get 4 into A within brackets 2n divided by n squared plus 1 minus 1, then that should be equal to 0 in order to have the minimum wetted perimeter with respect to the side slope. Earlier, minimum wetted perimeter was taken with respect to the water depth. Okay, water depth. And then now we have got the minimum wetted perimeter with respect to the side slopes. Now, when you do that one, when it is equal to 0, of course, A is not going to be a 0 quantity. So 2n divided by square root of n squared plus 1 minus 1 should be equal to 0. And this is going to give you n equals 1 over square root of 3. N equals 1 over square root of 3. Now, what is n equals 1 over square root of 3? What is that particular slope? What is this angle, or in other words? When n equals 1 over square root of 3, what is this angle? This theta. If this is 1 over square root of 3. This one should be 60 degrees. No? This one should be 60 degrees. Now just suppose that if this is the case, the side slopes are now 60 degrees. Side slopes are 60 degrees. And then what can you say about B? The value of B. B value. Can you calculate B? B. So B is this. B is this. We have got the value of B. B and side slope. B and side slope. B and side slope. What is the value of side slope? This side slope. This side slope. What is the value of side slope? I'll call this one L. What is the value of side slope? D square of L squared would be D squared plus D squared N squared. Okay, so this one would be then D squared, and N is now 1 over square root of 3. 1 over square root of 3. So this one would be 1 over 3, and L would be D, and this one would become 4D square divided by 3, and this would become 2 divided by square root of 3. What would be the value of B? What would be the value of B if that is the case? What is the value of B? B is 2D 1 plus N squared minus N. So 2D 1 plus N squared, square root of 1 plus N squared. N is 1 over square root of 3. So it would be 1 over 3. So it would become 4 over 3. 4 over 3 means 2 over square root of 3. And minus N would be 1 over square root of 3. And then this would become 2D divided by square root of 3. So B and this side slope L will be similar. So this one would become B. So which means now the side slope is also 60 and B equals this side slope. So the shape of this trapezoidal section, when you want to have the optimum section, it would be a half of a hexagon. No? So this length is equal to this length, and that is equal to this length, and the side slopes are of course now 60 degrees. Okay, 60 degrees. So it would make this trapezoidal section half of a hexagon. So remember that if you are looking at a trapezoidal section, the optimum section is given by half of a hexagon. Now it is not going to, I mean, these lengths can be the same without making this angle 60 degrees. Okay, that is also possible without making something like this, and then this can be 45, and then still you can have this L, this L, and this L, but it is not a it's not half of a hexagon. Half of a hexagon is when these are also equal to each other, and then when this angle becomes 60. So here in this case we have proved that these lengths are the same and the angle is also 60 degrees. So the optimum shape or optimum shape of the cross section, if it is a trapezoidal one, will be a half of a hexagon. Now, can someone tell me if this is the case? What would be what relationship can you expect for a rectangular cross section? Can someone answer that? What relationship can you expect for a rectangle cross section? By observing the results of a trapezoidal section, can someone answer that? What would be the shape of a rectangular cross section? Any relationship that you can think of? I would give you this equation with this one, because now this is without considering the side slopes, so only the water depth. So if you have a rectangular cross section, what can you say about the depth and the breadth? D and B, if it is a rectangular cross section. Can someone answer that? Can't?
D equal B divided by 2.
Ah, yes, very good, right? So it happens like this. Now, if it is a rectangular cross section, then n is 0, no? Because if it is a rectangular one, there is no side slope. So n becomes 0. The sides would be vertical. So that means n equals 0. So this is 0. And this is also 0. So that means the breadth will have to be twice the water depth. So if you are going to design a rectangular cross section, remember the optimum shape of that rectangular cross section, optimum flow will be when the breadth, or you can say when the water depth is half of the breadth. Okay, half of the breadth. Again, what you are getting is a circular, I mean, it's a circle, no? It's, if you take it, it's the circle that we are looking at. So this is this same circle. So this is the breadth and this is the diameter, and then diameter will be equal to the water depth, and this is also D and this is also D. So that means B equals to D. Okay, right? So rectangle, if it is a rectangular cross section, then it has to be the breadth equals 2 times the water depth, right? Okay. So that is about uh, a trapezoidal section and a rectangular section, and then you can think of applying this one to a triangular section, right? Try to do it by yourself. Try to apply the same concept to a triangular section, and then see what relationship you can obtain for a triangular section. Okay, right. Now I will take a circular section. This is a bit more interesting. Circular section, and even though this is a circular section, we are not talking about pipe flow. Here it's a circular section, but the water is flowing partially, right? Water is flowing inside the section partially. So this is the boundary. This is the boundary of the section. Okay, so this is the boundary cross section, and it is flowing partially. So it can be a Hume pipe, right? Maybe a culvert. So there can be a flow inside culvert. So in the culvert, generally you will find partially filled flow. It's not full flow like pipe flow. There can be certain situations where the flow in a culvert is also like pipe flow when you have flood conditions. But on a general day, the flow in a culvert may be a partially filled flow. So let's look at a flow condition. So this is your free surface in the circular cross section. The depth of flow is capital Z. Here I have taken the depth of flow as capital Z. Okay, depth of flow as capital Z. Right. Now, unlike the trapezoidal section, when I change the diameter of the pipe, basically, it is the main condition which would give, the changes to the area. No? Area of the section is dependent on the diameter. And if you take the water depth, okay, the flow area, this water flowing area, that flowing area is now dependent on Z, right? This flow area is dependent on Z because this boundary is basically fixed. Earlier in the trapezoidal section, I could change the slope, side slope, and then the water depth. Okay, side slope and the water depth. Now you are not changing the side slopes. Only variable, only quantity that I can change in the pipe circular section is Z. Now, whenever I change Z, both the cross-sectional area and the wetted perimeter will change accordingly. Okay, accordingly it will be changed. Earlier, if you can remember, I fixed the cross-sectional area, flow area, and then looked at how area would change with the water depth and then the side slopes. But here, I can't fix the area. I can't fix the area, flow area. The reason is this water depth will basically, make the flow area dependent on the water depth only. The reason is now there is no side slope to, change the area. Area is only dependent on the water depth. Now, when that happens, velocity and discharge can have different maximum values. Okay. When that happens, velocity and discharge can have different maximum values. I'll show you how. Earlier, since I have fixed the area, this A was basically a constant, and only dependent was the wetted perimeter. Now, if you take the circular section, the velocity is given by the chassis formula, and if you take the discharge, and that is given by area into this velocity. So you have AC, A divided by P to the power of half, I to the power of half. Now, when I change the water depth Z, both A and P will change. Both A and P will change. So now if I only consider the velocity, I only get A and P. A divided by P to the power of half. But when I get the discharge, I get A into A divided by P to the power of half. So I get another A which is dependent on the water depth. Earlier, I did not make A dependent on this water depth into the equation. Okay. So now what happens here is, this is my equation. I'll call this equation number 1. I'm going to look at the maximum velocity. Now, for the maximum velocity to occur, I know that then since I is a constant, C is a constant, A divided by P, okay, A divided by P should take a maximum value. A divided by P should take a maximum value. So what I'm going to do here is, I need to change the water depth. I need to change water depth. And now the water depth in this case, I have made it, dependent on theta. This theta, I have defined an angle theta, which would make the water level to go up and down. For example, when theta equals 0, water depth is 0. When theta equals 90 degrees, Z is d divided by 2, half of the diameter. When theta equals 180 degrees, Z equals capital D, or the diameter of the pipe. So now I'm looking at the maximum velocity. So for the maximum velocity to occur, using this equation, A divided by P should take a maximum value. So if it is going to take a maximum value with respect to this theta or the water depth, I have made theta as a dependent quantity for Z. So I differentiated A by P with respect to theta. So when I differentiate this one with respect to theta, this is how the differentiation of a division is done. You keep P, differentiate A, minus you keep A, differentiate P with respect to theta, and then you have to divide the whole thing by a square of the denominator, right? Denominator. And we know that P is not a negative quantity, and this is not going to be, sorry, P is not a zero quantity. So this is not going to be infinity or 0. So then P dA by d theta minus A into dP by d theta should be equal to 0 if it is going to be a maximum value, right? So what I have done here is I have done the substitutions for P and A using theta and R. So let's take P. What is the value of P? What is the value of P in terms of the radius of the pipe and theta? P is this length from here to here, that STU length, this length. What is the value of this one? What is the value of P or expression for P? Can someone guide me? Very simple. Arc length. Arc length. If this is R and if this is theta, the arc length would be R theta. So you have two sides. So this would become 2R theta. No? So the wetted perimeter for this case is 2R theta. And what is the cross-sectional area? 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 So what you need to do is you have to take this cake-shaped segment, cake-shaped segment, and then you need to subtract this triangular-shaped segment from the big section. Then you will get this area. Okay, this area. Okay, so that is the flow area. So what is the cake-shaped section? What is the area of the cake-shaped section? What is the area? Area of a circular segment would be half R squared theta, no? Half R squared theta. Now, since you have two segments, you have 2. So that is the bigger section. Bigger section would be half R squared theta into 2. Then what is the flow area? You have to subtract. You have to subtract the triangular area, not triangular area. So when this is R, this would be R cos theta, Okay. When this is R cos theta, and this is R sin theta. So you get half R cos theta into R sin theta. Since you have two segments, you have to multiply it by 2. Okay, so let's substitute that one, and then of course you differentiate sorry, you differentiate P and A, and then get dP by d theta and dA by d theta also using these expressions. Do the substitution, and if you do that substitution, you're going to get an expression only using thetas. Okay, only variable would be theta, and this is a non-linear equation. You can't simply solve it. It's a non-linear equation. You have sine, cosines in both sides, and then thetas, and then the product between theta and sine 2 theta. That's why it becomes a non-linear equation. So you can't simply solve it. It has to be from a numerical method, or you can use trial and error method. And if you do maybe a simple trial and error method, you will find that the theta will have to be equal to 128.75 degrees in order to satisfy this particular equation. Okay, in order to satisfy this particular equation. So when theta, I'm sorry, I'm getting a bit of a cough. Okay, so when theta equals 128.75 degrees, the Z, the water depth, will be 0.81 times the diameter of the pipeline. So the Z value, the water depth inside the pipe will have to be 0.81 times the diameter of the pipeline. So this is for the maximum velocity to occur along a circular pipe or a channel with a circular section. It is not flowing full. Even you can see that it is not flowing full. For example, if now if this is the pipe, basically what you have is this is D and the water depth is about 0.81 D. Okay, so this would be your free surface. To achieve the maximum velocity, the water depth will have to be about 0.81 times the diameter of the pipeline. Now, you can think of a maximum discharge, right? Maximum discharge, just like in the case for the trapezoidal section. Now, we know that A is dependent on the water depth or the theta. So I have to bring this A into this, the expression. A is dependent, A and P both are dependent on the water depth. So in that case, the maximum discharge, for the maximum discharge, I have to consider A cube divided by P. The reason is when you multiply the velocity expression by A, you get AC into A divided by P to the power of half, I to the power of half. And when you bring this A into the square root, then it would become A squared into A would be A to the power of 3. So now this whole thing will have to be a maximum one in order to have maximum discharge along the pipeline, right? So similarly, when you differentiate, you will get an expression 3p dA by d theta minus a dp by d theta equals 0, right? So again, it's the differentiation of a division, and then this is what you're going to get. And if you do the substitutions for P and A using R and theta, okay, the functions of R and theta, these are functions of R and theta. When you do that substitution for this particular equation, then you will get another expression or another equation using theta, which is different from the previous one. Of course, it would be different. And then you will find that the theta value in this case would have to be 154 degrees, right? So that means this theta will have to be 154. So 54, it's not 180. If it is 180, it would be flowing full. Theta will have to be 154 degrees. And if you look at it, 154 degrees will correspond to a water depth of 0.95 times the water depth, 0.95 times the diameter of the pipeline. So this is how or what you would get for the water depths when you have to consider the maximum velocities and the maximum discharges. Sometimes you need to have certain, velocities. We study about the maximum velocities in the channels. Generally, when you want to see, there is something called kind of a cleansing velocity. If there is a debris or some material and you want the material to, flow along that channel, and then we want to make sure that it has sufficient velocity along the pipeline. Discharge is the total quantity, and then certain velocities, particularly closer to the channel beds, and then we'll have to have a particular value. In order to study that one, we basically check whether it is at an appropriate level or not. So that is the reason why we looked at the maximum velocity and also the maximum discharge. Okay, is that clear? Any questions up to this point? So this is still we are at uniform flow, and we were looking at the optimum sections considering a circular section, okay, and a trapezoidal section. Okay. Of course, if this is the circular section, don't think that we are going to have very large sections. These are relevant to very small sections. particularly like Hume pipes, which can be basically brought from a yard, precast yard, and then installed or fabricated, installed, assembled in the site. Okay, we are not talking about large diameter sections, concrete or any material section which is constructed as big as a trapezoidal section. So it might be a small section that we are considering when it comes to the circular sections. Okay, right. So then I'll move to the next slide. Right. So that's a little bit about the uniform flow conditions. It's an introduction, some theoretical background on uniform flow. Now we will look at the non-uniform flow. Now, what is the difference between the uniform flow and non-uniform flow? Uniform flow and non-uniform flow. So if you take a particular channel, here we are looking at channel. Okay, we are looking at steady flow. So that means if you take a particular point, the velocity at that particular point, flow velocity, will be constant, or it doesn't depend on time. If you take a particular point, that is steady flow. Now we are considering a flow. If you take a particular point, at that point, velocity will be constant. And then if you take another point, the velocity will be different, but with respect to time, at that particular point, that velocity is constant. So different values, but with respect to time, it would be constant. So that is the steady flow. The non-uniform flow means along the channel, that is in space, not with respect to time. Now with respect to space, if you have a steady flow, if the velocities are different at different points, then the flow will become a non-uniform flow. When you have different velocities, that means something is different in the channel section, right? That's how the velocities can be different. Otherwise, if it is the same cross-sectional area, basically, if it is the same cross-sectional area, and if it is the same slope, then both all points will have to have the same cross-sectional area for the flow, hence should have the same velocity, because the flow is steady. According to continuity, then velocities will have to be the same. If the velocities will have to be the same, then the water depths will be also the same. Now, in non-uniform conditions, there can be certain changes to the channel section. There can be certain changes to the channel bottom, and this would make even a steady flow a non-uniform flow along the channel. So the flow is still steady, but along the channel, due to certain destructions, the flow will become non-uniform. Okay, non-uniform. In the study of non-uniform flow, we basically look at what we call the gradually varied flow, and rapidly varied flow. Now, this particular diagram, okay, these diagrams, so I'll take the first one. This particular diagram will show you the occurrence of gradually varied flow, the possibilities of the occurrence of gradually varied flow along a channel. Now you will see that this channel bottom is not even. Now see here, it's not constant. Slope is not constant. It's changing. So this will lead to some changes to the water levels. And if there is a sudden change, of course, the water levels can change rapidly. So here you find some rapidly varied flow. Now it cannot become suddenly constant. Okay, the water depth cannot be suddenly constant, and it would take a kind of a transitional region, and then there can be a gradually varied flow from this rapidly varied section. And then if you have a sluice gate like this, there can be a kind of a ponding effect on the upstream side, and that can lead to high water levels upstream of the sluice gate. Now, since this is coming at a high speed, and then this is becoming kind of a pond, then there would be a kind of a transition which would relate to a rapidly varied flow. The water depths will become high, or the velocities will become smaller starting from a high velocity. So you can observe something called a rapidly varied flow in that condition. Now, in the upstream of the sluice gate, you won't see, a straight or parallel water level to the bottom because of this non-uniform condition. And then just above the sluice, upstream of the sluice, there can be a gradually varied flow. It's not parallel to the bottom. And then when you have a sluice, of course, it obstructs the flow, and then since you have a steady flow condition, here you have a flow Q, and then the same flow should be occurring below the sluice. And then this would lead to very high velocities, but until it reaches some changes to the conditions along this slope, the water will flow at a particular velocity with a very small water depth. Still, the flow condition would be a gradually varied flow. And then we know, we will study later, and if you have another ponding effect in the downstream, then this can go at a very high speed, and this would be very high speed, very high velocity, and then this would lead to a very low one, and then you can have another rapidly varied flow in between. So depending on the shape of the channel or the obstructions, the bottom slopes, the flow can be different from the uniform flow conditions, which can be non-uniform, and the non-uniform flow can be either gradually varied flow or rapidly varied flow. Under rapidly varied flow, we will basically study about the hydraulic jump. Possibly, you might have studied a little bit about the hydraulic jump when you were in level 4, or maybe when you were in level 3 when you were studying hydraulics and hydrology. But we will look at the occurrence of a hydraulic jump again, and then see the properties of a hydraulic jump. So under non-uniform flow, what you're going to study is gradually varied flow or rapidly varied flow, right? So first we will look at the gradually varied flow. And before I move to a gradually varied flow, I want to highlight some terms that would be useful in the analysis, right? In gradually varied flow. Now this is a channel which is having a bottom slope S0, channel bottom, and I'm considering 2 points between 1 and 2, and the distance between the 2 points would be delta x, and bottom slope is denoted by S0, and then the friction slope is denoted by SF. That means the difference between the total heads, right? We know. We have learned about the energy grade line. Energy grade line is a representation of the total head. Energy grade line actually represents the total head. Now, if I take this one, if this is the datum, and if I take a point here, the total energy at this particular point at the channel bottom would be Z1 plus Y1. That is, this one would be Y, no? The water depth. Pressure head would be Y at the bottom. So Z plus Y plus V square divided by 2G. Is Y plus Z plus V square divided by 2G would be your total head. So if it is 0.1, it would be Y1 plus Z1 plus V1 square divided by 2G. If it is 0.2, it would be Y2 plus Z2 plus V2 square divided by 2G. So that is your total head. And the total head is represented by the energy grade line. Now let's take the piezometric head. Piezometric head is ignoring the velocity head. Piezometric head. Pressure head plus the datum head. Now if I take a particular point here, what is the piezometric head? it would be Z1 plus Y1, no? Or Z1 plus P1 divided by rho G. At point 1, it would be, this one would be P1 divided by rho G. P1 divided by rho G. Now, what does it represent? What does it represent? Piezometric head. The piezometric head represents the hydraulic grade line. No? Piezometric head represents the hydraulic grade line, excluding the velocity head. Now, can you find a nice, relationship between the hydraulic grade line and the free surface? They coincide, no? So in open channel flow, remember in open channel flow, the hydraulic grade line actually coincides the free surface. This is free surface. So very nicely, it coincides the free surface. Hydraulic grade line represents the piezometric head and it coincides the free surface. Total energy is represented by the energy grade line. It is always going to be above the free surface because there is velocity head as well. Now there is another term called specific energy. Sometimes it is called specific head. Actually, it's not energy term. It's a head term. It's a head term. If you look at it, measured in meters, the specific energy is defined as the energy above the bottom, something like that. Energy above the channel bottom. So energy above the channel bottom means the water depth or the pressure head plus the velocity head. No, the head above the channel bottom is the pressure head or the water depth plus the velocity head. So water depth plus the velocity head. So that is the specific energy or the specific head, right? So some information, some definitions with respect to the open channel flow. Right, now we are going to look at the non-uniform flow. Non-uniform flow. And in non-uniform flow, if I consider this specific energy, you will find that the specific energy is given by D plus V square divided by 2G, as I have told you earlier, right? As I have explained earlier, the specific energy or the specific head is given by the water depth plus the velocity head. Water depth here, now I have denoted by capital D. D plus V square divided by 2G. Now, if I take a rectangular cross section, I'm checking a rectangular cross section. Rectangular cross section. Okay, I'm going to take a rectangular cross section. The water depth is D. The breadth is B. And if the discharge is Q, if the discharge is Q, Q is equal to V bar into B into D. No? Cross-sectional area would be B into D. B into D multiplied by the velocity will give you the discharge along the channel. And the discharge per unit width, generally this is denoted by simple Q, and that is simply V bar into D. Right? We also know this one. Q divided by B is the discharge per unit width, which is denoted by capital simple Q, and it is equal to V bar into D. Right. So let me do the substitution now here for the velocity. The velocity is Q divided by BD, right? So V squared then would be Q squared divided by B squared D squared. And then you have to divide it by 2G in order to get the velocity head. Now, Q squared divided by B squared would be Q squared. So the specific energy now written in a different form, specific energy, that is D plus Q squared divided by 2G D squared, right? Specific energy is now drawn, written in a different form, that is the D plus Q squared divided by 2G T squared. Now suppose that you have a constant flow rate, okay, constant steady flow rate, And what would be the variation of this specific energy with respect to the water depth? Now, how do I, observe or investigate the specific energy, variation of the specific energy with respect to the water depth? Now, see, this is E, and I'll take this one as E1, and I'll take this one as E2. Okay. This is to graphically represent E. So E, capital E, this is the specific energy. I divided them into two. One is E1 and the other one is E2. Now, let me plot E in the horizontal axis. So I'll plot E1 with respect to D. Now, what would be E1 versus D curve? What is E1 versus D curve? Can someone tell me the shape of the E1 versus D curve? E1 versus D curve. Can someone tell me? E1 versus D curve. What is the shape? E1 versus D curve. What would be the shape? E1 is D, no? E1 now is D. E2 is Q squared divided by 2G T squared. What is E1 versus D? I need an answer. How would it look like? E1 versus D.
Y equal mx.
Yeah, y equals mx. Very simple. A straight line. And then it would be passing through this one. And then the gradient will be 45 degrees. No? So this is E1 versus D. This is E1 versus D. Now, how about E2 versus D? E2 versus D. So, E2 versus D. E2 versus D, what would be the shape? Now you can argue. No? When D equals 0, when D equals 0, then E2 should be what? When D equals 0.
Maximum.
Huh?
Maximum.
Maximum means when D equals 0, infinity, no? It has to be infinity, no? Right. And then when D equals minus infinity,
E to 0.
E2 equals 0. When D equals minus infinity, E2 equals 0. So let me draw both E2. So when D equals minus infinity, so that is somewhere here, E2 equals 0, no? E2 equals 0. And then when when D equals 0, then this would be, again, this would be 0, no? Correct? Sorry, infinity, right? So then from in the minus segment, the shape of the curve would be something like this. So when D equals negative, how about for positive values of D? Positive values of D. When D equals positive value, what is that curve? When D equals positive. D equals positive infinity. E2?
0.
0. So here, no? Okay. And then D equals 0 again, infinity, no? So in the positive segment, you have something like this. Now think about the summation. Of course, this is useless. The reason is water depths cannot be negative. Now the summation of these two curves, E1 and E2 curves for a given water depth will give me something like this. I'm going to do it with a maybe different color. So it's going to give me the summation. 0 plus infinity would be infinity. 0 plus infinity would be infinity. And then you will have a curve like this. Okay. So this one has a curve something like this. It's something like this. So this is E versus T curve. So what I have done here is I plotted E1 and E2 separately and got the cumulative effect. So E, the specific energy versus water depth, will give me something like this, right? Something like this. So if I take a particular specific energy, it is related to two water depths. See, D1 and D2. So if I take a particular specific energy under a constant Q value, it is related to two water depths. Okay, two water depths. And there is a point where the solution will have only one. Okay, that is the minimum one. This is the minimum one. So this represents the minimum specific energy. Okay, so this is the minimum specific energy, and we call this one the critical depth. Okay, critical depth. So the water depth which corresponds to the minimum specific energy is called the critical water depth. Critical water depth, right? Critical water depth. And any other one would be having two water depths for a given specific energy. Only for the critical conditions you will get one water depth. Other than that, in non-uniform flow, basically for a given specific energy, it can have two water depths. Okay, you're talking about the same specific energy, the same discharge. That means you can have two water depths depending on the flow conditions. So remember that for a given specific energy, it can have two water depths, corresponding water depths. So the solution will have two water depths. Now, how do we find the specific, the minimum specific energy or the critical depth? When your the specific energy is given by E equals D plus Q squared divided by 2G D squared, the minimum one means this one has to be equal to 0. No, for critical conditions, dE by dd should be equal to 0. So let's differentiate this equation. I'll call this one equation number 1. Let's differentiate this equation with respect to d. So if I differentiate this one with respect to d, this would become dE by dt, and that would be equal to 1 minus, because this is square term, and it would become q squared divided by g d to the power of 3. Now, since these are related to the critical conditions, this is the minimum one, and then this d is now your dc value. Okay, dc value. So 1 minus q squared divided by gdc, critical one, will be equal to 0, right? Equal to 0. And then dc, according to that one, will become q squared divided by g to the power of 1/3. So the critical water depth can be computed using the discharge per unit width. Okay, if you know the discharge per unit width along rectangular cross section, you can find the critical water depth, and then do this substitution here. And then you will find that the minimum specific energy, this minimum specific energy will be 1.5 times the critical water depth. for a rectangular cross section. So remember, this analysis, whole analysis which I have performed is only relevant to rectangular cross sections. Rectangular cross sections. You can't apply that one to any other cross section. This is only relevant to rectangular cross section. If you want to go ahead with any other section, then you have to start with the initial conditions and then do the derivation accordingly, right? Q divided by BD only applicable for velocity when it is a rectangular cross section, and if you have a trapezoidal or triangular section, then the velocity will not be given by Q divided by BD. So it could be a different expression. So accordingly, you have to write the expression for the specific energy and then get the maximum minimum value by differentiation, and then do the substitution and get the values accordingly. So you will get different expressions for different cross sections. Right, so this is for a rectangular section, and then of course you can do this one for any non-rectangular section. Okay, non-rectangular section. So we know that the critical, the specific energy is written as d plus v square divided by 2g, and then we know the velocity is the discharge divided by area. Do that substitution. Now we are not going to write it like q divided by the b into d, and this is not the case for non-rectangular section. So you have to write q divided by a. E then would be equal to d plus q square divided by 2a squared into g. Okay, so for the minimum specific energy, dE by dt should be equal to 0. So if I differentiate this one, this would become 1 minus 2q squared a to the power of minus 3 divided by 2g into dA by dd. So dA by dt at the surface will be basically, so this is cross-sectional area, okay, cross-sectional area, d delta A into B, sorry, delta D into B will be delta A. So B is delta A divided by delta D, or in other words, you can say this is dA by dd. So when you substitute that one here under critical conditions, for the minimum specific energy, that is minimum specific energy, that means the critical flow conditions, q squared b divided by a cube g should be equal to 1 for a non-rectangular section. So you can directly use this one for trapezoidal section or triangular section if you want, rather than going starting from the the first principles. Right, now the critical conditions can occur. I told you that in channels there can be different changes in the channel section or the bottom. The critical conditions will occur when the water levels change from a high, in a way, high water level to a low one. Now critical depth corresponds to the minimum specific energies. Now if I take a rectangular section, so this is E and this is D, and I told you that for a given specific energy there are two water depths, and this is your critical depth. When the water depth along a channel, is greater than the critical water depth, we call this one the slow flow or the tranquil flow. So slow flow or subcritical flow. And when the water depth is less than the critical water depth, we call this one the supercritical flow or the fast flow. Okay, fast flow or supercritical flow. So this critical water depth actually separates the flow into supercritical or subcritical. Supercritical means when the water depths are less than the critical depth for a given channel. The subcritical flow means the water depth is greater than the critical water depth. Now, when you are given a particular discharge, okay, discharge per unit width for a given channel, if the cross section is rectangular, we can easily find the critical water depth, and that is given by Q divided by G, and this one. So the critical water depth is given by Q square divided by G to the power of 1/3. That means for a given discharge, steady discharge, DC is a fixed quantity. So you know that this is going to be a fixed quantity for a given channel. And this one only is relevant for rectangular one. And if you have a trapezoidal one, if you have a triangular one, you will have different expressions for DC, right? So if it is a rectangular one, this is the expression for DC. This is how we can find DC using the discharge. So now in channels, if you have differences in the slopes, then you might come across critical conditions due to the changes in the water depths. Now this is the critical depth. Okay, critical depth, you can see that this is the dashed line. Critical depth identified for a given discharge along possibly a rectangular cross section here. But you will see that there are differences in the bottom slope. Now this is going to make the flow non-uniform. Now when you have a mild slope, the water the velocities will be fairly mild, and that would lead to a larger water depths. Possibly it can be even larger than the critical water depth. If you make the bottom become steeper, then the velocities will become higher. That would lead to a lower water depths, and that water depth can even go below the critical water depth, just like that you find here. So here you will find that the water level crosses the critical water depth. Critical water depth is a kind of a virtual quantity here, and you will see that the water level crosses the critical depth. So here what you find is a critical condition. And at the same time, if you have a channel again becoming a mild section, then here you will have supercritical condition, and then again you might have subcritical. So this is subcritical because the water depths are high, and then here you have supercritical flow, and here also this is a subcritical flow. So there can be different flow regimes in terms of the condition, whether it is going to be subcritical or supercritical. In between, if there is a transition, that means the critical conditions occur. Now this is one example where you have a transition from tranquil to shooting, and then shooting to tranquil, okay, or subcritical to supercritical, and then supercritical to subcritical. In both cases you will find the occurrence of critical water depth. And then this is from a reservoir most probably into a channel of steep slope. Then again the water levels just above the channel may be subcritical, and then along the channel there can be supercritical flow depending on the slope. Okay, if the slope is fairly high, then it can lead to supercritical flow. So then this means the critical depth occurs. And at the same time, just like in a waterfall, there can be some flow, free outfall from a channel, and then it can also lead to the occurrence of critical conditions. So critical condition occurs somewhere here, okay, somewhere here. Oh, yeah, somewhere here. Okay, so critical conditions occur somewhere here. So critical conditions can occur due to various reasons, particularly or mainly you can say that it is due to channel bottom. Okay, due to the different shapes of the different steepness of the channel bottom. Right, now In non-uniform flow, I told you that we will be looking at the gradually varied flow and the rapidly varied flow. And we need to do a little bit of analysis using the first principles for the gradually varied flow in order to trace the water level. So here, this is for a gradually varied flow. It's not for a rapidly varied flow. No occurrence of uh, basically critical conditions here. We are not considering about supercritical to subcritical or anything like that. We are considering a simple gradually varied flow where the water surface will not rise or drop rapidly, a gradual change along the channel. So let me consider this particular diagram where I have considered point A and B, which are close to each other, and the distance between these two would be delta L, delta L. Now, if the channel bottom slope is simple L or S, sorry, simple S, this level height is going to be S into delta L. Now, the horizontal distance is delta L, and if the slope is given by simple S, this level difference would be S into delta L. The height of A, bottom A, above bottom B would be S into delta L. So let me take this one as the datum, okay, datum, and write the Bernoulli's equation with the incorporation of head loss, between point A and point B, Now, what is the datum head at point A? Datum head at point A, it would be S into delta L. Huh? Okay, I'm considering this particular point. S into delta L would be the datum head at this particular point because your datum is here. The pressure head is P divided by rho G. P divided by rho G equals to capital D. And the average velocity at this particular point, let's say this is V, okay, or V bar. Okay, V bar. So V bar square divided by 2G will give me the velocity head at point A. Now I'm going to consider a change to the free surface. Now it is not uniform flow, non-uniform flow. So some changes occur when the fluid flows from point A to point B. Now when that happens, I'm going to assume that there is a change of delta V to the velocity and a change of delta D to the velocity. You might wonder if this is a positive quantity, then this one should be a negative quantity. No? Now let's forget about that one. We don't know the magnitude of delta D and delta V. We just want to say that there is kind of a change to the velocity at point B compared to point A due to this non-uniformity along the flow. So V plus delta V would be the velocity at point B. Accordingly, the water depth at point B would be D plus delta D. So I'm going to apply the Bernoulli's equation again. Now the datum head is 0 at this particular point. And the water depth is now D plus delta D. And this is the pressure head. Pressure head is D plus delta D. Since water depth is D plus delta D. The velocity head would be V bar plus delta V bar squared divided by 2G. So this is your velocity head at point B. Now, since I have considered the friction head loss, and if the friction gradient is I, friction gradient is friction head loss divided by delta L, right? So then friction head loss divided by delta L multiplied by delta L would give me the friction head loss. So this is actually friction head loss. So I have to add that one to the point B. So I have added that one. And here you will see that when I expand this term, expand this one, I'm going to get V bar squared plus 2V bar delta V bar plus delta V bar squared. Okay, and that divided by 2G. Now, if you look at the magnitudes of these terms, delta V is a small quantity, square of delta V would be a very small quantity, and I'm going to ignore these higher order terms. So I got V bar squared plus 2V bar delta V divided by 2G here. And then at the same time, I had D plus delta D here. Now, when you look at the left-hand side and right-hand side, this D to this D will be cancelled off. This V bar squared divided by 2G to this V bar divided by 2G will be cancelled off. So I would have S into delta L on the left-hand side, then this delta D on the right-hand side plus V bar delta V bar divided by G, because 2 will be cancelled off, plus I into delta L. I into delta L. And what I have done here is I have done a small rearrangement of the terms and got delta D by delta L on the left hand side. So when I do that, delta D by delta L will be equal to S minus V bar delta V bar divided by G delta L minus I. Right? So one expression, I'll call this one equation number 1. Now this is supply-Bernoulli's equation, energy. And if I consider now the continuity, then the velocity, because the cross-section is the same, right? Same cross-section. I take rectangular section. V into D, velocity into the depth, into B, of course. You have a B here, okay? Another B here. Both are the same. V into D should be, this is V bar into D should be equal to V bar plus delta V into D plus delta D. Now, similar to the previous one, I can expand this one. I have V bar D plus V bar delta D plus delta V bar D plus delta V bar delta D. Now, since delta V and delta D are small quantities, second order quantities can be ignored. And then VD to this VD will be cancelled off. And I'm going to get delta V. I can take delta V bar to left hand side. Delta V will become minus V bar delta D divided by D. So this is using the continuity. So let me now substitute this delta V in equation number one, and then write my equation. So if I write the equation number 1, okay, equation number 1, by substituting equation number 2 in equation number 1, I'm going to get delta D divided by delta L equals S minus I plus V square divided by GD into delta D divided by L. So delta D divided by L is common here and here. So I'm going to take this one here. So it would become 1 minus V square GD, 1 minus V square divided by GD into delta D by delta L, and that is going to be equal to S minus I. S is the bottom slope, I is the friction slope. So this is going to give me delta D by delta L equals S minus I 1 minus V square divided by GD. Now you will see that D corresponds to the vertical, dimension, that is the water depth, and L corresponds to the horizontal component. So you can sometimes see in books something like this. Delta D by delta L is in differential forms, it would be dy by dx, and S is the bottom slope. Bottom slope is denoted by S naught. Friction slope is denoted by SF. And this one is actually 1 minus square of the fruit number. No? Fruit number, we know that fruit number is the square, fruit number is V divided by square root of GD for open channel flow. You all know that the fruit number is a kind of a dominant non-dimensional quantity when it comes to open channel flow. So the profile of the non-uniform flow when you find gradually varied flow will be given by this dy by dx equals S0 minus SF divided by 1 minus square of the fluid number. So if you know these quantities, you can find this slope. You can find the slope of the water surface, and you can trace the water surface if the flow is non-uniform. Now, if you look at this one, if the flow is uniform, we know that the friction slope equals the bottom slope for uniform flow. So this would become, the numerator will become 0 for uniform flow. That means dy by dx will have to be equal to 0. That means the water surface is parallel to the bottom. Okay, water surface is parallel to the bottom. So this is the analysis that you perform for gradually varied flow. Right. So how much of time do I have? Okay, I have another 20 minutes. So I will go through with this one. Now, this is something to do with the classification of water surface profiles for non-uniform flow. And when you have non-uniform flow, there can be various conditions. Now, the water level is not parallel to the bottom slope, and it can have different, profiles. dy by dx can be greater than 0, and dy by dx even can be less than 0. dy by dx equals 0 when the flow is uniform. Okay, when the flow is uniform. In other conditions, it can be either positive. Positive means a profile like this. Negative means a profile like this. Now, there are different conditions you would come across, and they are classified with respect to the water profiles and the bottom slope. Now, let me take one example. You can go through with the different conditions. I will take one example. I'm going to take what we call the mild slope. Now, the mild slope is defined like this. When you have a given flow, okay, QO, simple QO, capital Q, if there is a particular bottom slope, there would be a water depth corresponding to that bottom slope. Now, if you take Manning's equation, m to the power of 2 divided by 3, and S0 to the power of half. So this is into, this is Manning's equation for the discharge. So if you take a particular discharge, and having known the bottom slope and then the Manning's coefficient, there would be a particular water depth corresponding to that particular discharge. And we call that one the normal depth. So the normal depth is the water depth in a channel when the flow is uniform. So if you have a particular channel with a constant cross section, let's say you have a rectangular cross section, there would be a water depth corresponding to uniform flow, right? So if you assume the flow to be uniform and it would take a particular water depth, so we generally call it the normal water depth. And at the same time, along that channel, if the conditions become critical, it would have a specific virtual quantity called critical depth. Now, suppose that that critical depth, the computed critical depth, is less than the normal depth. If the critical water depth, computed critical depth, is less than the computed normal depth for the given flow, the channel slope is considered to be mild. Okay, the channel slope is considered to be mild. Now, in this case, you will clearly see that the critical depth, the virtual quantity critical depth, is less than the normal water depth, right? Now, when you have something like this, there are three regimes. I'll take this one as 1. I'll have 2 and I'll have 3. So there are 3 regimes where the water profile can take. The first one is denoted by M1 profile. We call it M1 profile. That is when the water depth is greater than the normal depth. Of course, it will be anyway greater than critical water depth. So we identify this one as M1 profile. And when the water depth along the channel, that non-uniform flow, the profile is between the critical water depth and the normal depth, it is having M2 profile. And if the profile is having a water depth which is even less than the critical water depth, then we call this one M3. So similarly, when the critical water depth is greater than the normal depth, we call the slope to be steep. And when they are equal to each other, that means the critical water depth equals the normal water depth, we call it the critical slope. And then there can be 2 other conditions where the bed become horizontal and there can be an adverse slope, negative slope. In all these 3, mild slope, steep slope, and critical slope, the slope is in the downward direction. Horizontal means it's flat. Adverse slope means the slope is now negative. Now see here, you will find that it says the normal depth is infinity. Normal depth is infinity. Can somebody tell me why normal depth is infinity in horizontal bed and adverse slope? Any particular reason why normal depth is infinity in horizontal bed and in adverse slopes? Now, normal depth is not defined for horizontal beds and adverse slope. If you can recall your memory, normal depth corresponds to the flow if the flow is uniform. And if the flow is uniform, we have very clearly explained that the bottom slope should be equal to friction slope. Now, if the bottom slope is 0, then friction slope is also then 0. Then that means the normal depth, the uniform flow cannot be defined. So in adverse conditions or horizontal bed conditions, the uniform flow cannot be defined. The reason is that the bottom is 0 and then the bottom is negative. So if you try to use the Manning's equation, then this would get a negative, this would S0 will get a negative quantity, right? And then or 0 quantity, and then which is not going to be possible for uniform flow, right? So that is why under horizontal bed and adverse slope conditions, the normal depth is not defined. Now I'm going to take this mild slope condition, and then see how I could say that this is increasing and this is decreasing and this is also increasing. So this is having dy by dx positive, and this one is having dy by dx negative, and this one is again having dy by dx positive. Okay, right. So let me take M1 curve. According to the definition, the normal depth is greater than the critical depth in the profile M. And if you take M1 curve, the water depth is even greater than the normal water depth. Now, according to my analysis for the gradually varied flow, dy by dx equals S0 minus SF divided by 1 minus Froude number to the power square of the Froude number. So let me say the denominator is x and numerator is x and the denominator is y. And I want to see the magnitude, then the sign of x and y accordingly. Now, Froude number like this, Froude number, this is Froude number. Froude number is given by, look at this expression, Froude number is given by q squared divided by g y a squared. You can easily find why this is the case. This is v squared divided by gy. So it is the square of Froude number. And according to the Manning's equation, under non-uniform conditions, the velocity is 1 over n m to the power of 2 divided by 3, friction slope to the power of half. When the flow is uniform, then friction slope becomes bottom slope. Now, if that is the case, friction slope by rearranging the terms can be written as n squared q squared p to the power of 4 divided by 3 divided by a squared 10 divided by 3. Now, if you look at any increase in y will make the Froude number to go down. The reason is y is highly dependent on a is highly dependent on y. So for a given discharge, Froude number goes down when y goes up. Okay, Froude number goes down. Now, if I look at the friction slope, when y goes down, both P and A goes up. But this dependency of A is more significant or more sensitive to y than P. Okay, so A is more sensitive to D, because this is 10 divided by 3, so more sensitive. So that means when y goes down, friction slope will also go down. So if y goes up, Froude number will go down and the friction slope will also go down. So if that is the case, when y is greater than yn, that is under this condition, in this region 1, that means the friction slope should be less than bottom slope. If it is exactly at this particular point, okay. So if you are somewhere here, then your friction slope equals bottom slope. But if you are going a little bit beyond the normal value, and if the depth is just greater than normal value, that means the friction slope will go down. And this is also correct. Y is anyway greater than yc. That means the Froude number will also go down. So according to this expression, S0 minus SF should be positive quantity if SF is less than S0. And Froude number is less than 1. Okay, Froude number is less than 1. Square of the Froude number will also be less than 1. Then y is also a positive quantity. So positive quantity divided by a positive quantity will lead to a positive gradient for the water profile. So that is why M1 profile is going up. Okay, M1 profile is going up. So similarly, you can look at the M2 curve. I'm going to leave this slide. You can check the video how it is done, and you will find that in this case again y is going down. When y is going up, we know that Froude number goes down, friction slope goes down. Now earlier, when you are here, friction slope and bottom slope, they are equal to each other, and if the water depth goes down beyond, goes down from the normal water depth, that means the friction slope should be greater than S0. So that means X would become a negative quantity, but still Y is greater than YC. So you are within this region. Okay, Y is greater than YC. So Froude number will still be less than 1. So this quantity 1 minus square of Froude number will be a positive quantity. So negative quantity divided by positive quantity will lead to a negative quantity. So that means the profile should have a negative slope, right? So similarly, you can argue for M3, and M3 again will have a negative quantity at the numerator and negative quantity at the denominator, which would lead to another positive quantity for dy by dx, and that is why M3 curve will go up. So similarly, for different slopes, you can argue in this manner and then explain how the profile would change along the flow if you have non-uniform, gradually varied flow. Okay. Right now, the analysis of the hydraulic jump is something that you have done previously under level 4 or level 3, okay, depending on the course that you have taken. And that analysis is very simple. The occurrence of the hydraulic jump will occur when flow changes from supercritical to subcritical. So if the flow changes from supercritical to subcritical, we know that there is going to be a critical condition. So critical depth is crossed, right, within the hydraulic jump. And hydraulic jump represents a very nice rapidly varied flow within a very short distance. Within a very short distance, the flow changes from supercritical to subcritical, which would lead to a increase in the water depth. So supercritical, under supercritical flow, the water depth will be less than the critical water depth, but in the subcritical flow, the water depths will be greater than the supercritical water depth. Now, in this case, we are not going to consider the energy balance. We can't consider the energy balance because in a hydraulic jump, there would be high dissipation of energy. So I cannot directly use Bernoulli's equation with a known expression for energy. So I'm going to use the continuity equation and the momentum equation. So this is the momentum equation for a control volume. Okay, control volume. So this is your control volume. This is the whole control volume that you consider. So apply the momentum equation for steady flow. So if the steady flow is considered, so this term disappear for the steady flow. So that means M in minus M out, this is the momentum flow rate, should be equal to minus sigma FCV. So the forces acting on the unbalanced forces acting on the control volume. Now, if I take the momentum flow rate in minus momentum flow rate out using continuity equation and the rho qv, so this is the momentum flow rate, rho qv, and if I do that substitution here, I get the difference between the momentum flow rate in and momentum flow rate out, and then I can also write the resultant the pressure forces acting on this control volume, and when I equate that one, I can get a relationship between the water depth, the supercritical water depth and the subcritical water depth. We call them the conjugate depths for the rapidly varied flow or the hydraulic jump. Conjugate water depth, complementary water depths, or complementary conjugate water depths, and then alternative water depths. We call them the alternative water depths. There is a relationship between D1, D2 and D1, and that is going to be given by this. If you reduce the form, and you can get this expression. And what you are seeing here is in a way D2 equals half D1 minus 1 plus square root of 1 plus 8 Froude number at 0.1 squared. Okay, right? So V1 bar square divided by GD1 is actually the Froude number at 0.1. So this is the relationship between the conjugate water depths or the alternative water depths of a hydraulic jump. Now in the hydraulic jump, I told you that there is high energy dissipation, and if you assume the bottom to be in a way flat, right? So this example is from a spillway. So at the toe of the spillway, you will generally find the occurrence of a hydraulic jump. And if you balance or get the difference of the total energies at point 2 and point 1, you can find the loss of energy in the hydraulic jump. Now, if this bottom slope is very mild or nearly flat, then basically the datum head will be the same for both the points. So you can ignore the datum head. So then the loss of energy would be coming from the specific energies. Okay, specific energy E1 minus E2. So the difference in the specific energies will give you the loss of energy in a hydraulic jump. Now, in the hydraulic jump, you know that the flow changes from shooting flow or supercritical flow to subcritical flow. So if you observe this particular we call it ED curve or EY curve, what happens here is when you have the occurrence of a hydraulic jump, rapidly varied flow, this doesn't change along this profile, nice profile. If it is a gradually varied flow, then this can change very nicely along this profile. But if it is a rapidly varied flow, since there is a change in the energy or loss of energy, this basically jumps rapidly from here to here. So if I take these points, okay, so this difference relates to the loss of energy. So what happens at hydraulic jump is it changes from a high specific energy to a low specific energy, high specific energy to a lower specific energy. So this is the specific energy, high specific energy to a low specific energy, and at the same time it changes from supercritical flow to subcritical flow, right? It doesn't change like this, right? Okay, energy is not conserved. If the energy is conserved, then this one should move like this, right? Because the specific energy will be now conserved on a flat surface. It doesn't happen that way. In the occurrence of hydraulic jump, there would be a loss of energy. So there would be a change from high specific energy to a low specific energy, from shooting flow to a tranquil flow, or from supercritical flow to a subcritical flow. So this is how you explain the occurrence of a hydraulic jump or the characteristics of a hydraulic jump using this ED diagram or EY diagram, right? So this is something to do with the rapidly varied flow, right? So that is what I need to cover under non-uniform flow in open channels, right? Non-uniform flow in open channels. And if you have a question, you can ask me, right? We will work out a few questions. I think I have shared with you the first assignment, and that assignment contains a few questions on uniform flow, non-uniform flow in rapidly varied conditions or gradually varied conditions, and when you have certain obstructions along the channel, drops, etc., and how flow changes from one condition to the other one, etc. And you can try the assignment, and then hopefully I would be able to work out those questions in an online session like this before continuous assessment test 1. Okay, right? Any questions? Right, no questions. Now, I don't need to share the presentation. The reason is I generally, share the video. Since I share the video, I generally don't share the presentation slides. If you want, I can share it in a slide mode, handout mode. Okay. Okay. If you really want it, then I can share it in the handout mode and then make a PDF and then upload. Okay. right? So for the continuous assessment test one, now I don't know now. Last week I was with the impression that the continuous assessment test would be conducted on campus. Now I don't know, maybe there is a discussion to conduct it online. Still we haven't heard of the mode, okay, whether it is going to be online or physical, held at the campus. So we will wait for another couple of days and then see how the continuous assessment test one is going to be conducted. Okay, right. So up to this point, it was my responsibility to take you through. Possibly after continuous assessment test one, after the continuous assessment test one, after the continuous assessment test one, most probably another lecturer will take over this particular course. Okay, right? So after continuous assessment test one, another lecturer will take over this particular course. I will continue to teach mechanics of fluids, but hydraulic engineering 2 will be taken by some other lecturer. Okay, I won't be available. Right, and it is the case for Cvx5241 as well. So it would be taken by some other lecturer after continuous assessment test one. Okay, right. So then let me stop the class now. If you don't have any other questions, okay, I'll share the video possibly tomorrow morning. Okay, then no questions.
Sir, excuse me. Critical line එකක් තියෙනවනේ උඩ. කලින්
Which one? The last slide or what?
No, sir, I am talking about
Which
it
slide?
may be two or three slides before the last slide.
Is it this one?
Sir, that is a critical line. Flow you saw us a critical line.
This one? Critical lines?
Right, this one.
Yeah.
So, the critical depth, the critical line is crossing the water flow line, no?
It's not.
No. I am
yes.
talking about critical depth.
Critical
there
depth.
is a two or three places. The critical depth is crossing the water flow line.
Yes, correct.
Water.
So if you take this one,
I am asking about those are equal.
Critical water depths. You want to know whether the critical water depth is the same or not?
Yes, sir. The crossing line.
Yeah, it is the same. The reason is now. Now if we are talking about trying to get can't get the pen. I don't know why. Now if you take where is it doesn't show my pen. Now if you take critical now if you take channel flow, okay, suppose that you have open rectangular channel, okay, flow in a rectangular channel. It might be having a particular steady discharge, okay, steady discharge. Now we know that for a given channel, if you have a particular discharge, the critical depth is given by, for a rectangular channel, Q square divided by G to the power of 1/3. Okay, when Q is constant, G is constant, then DC has to be, the critical depth has to be constant, correct? So it's a kind of a virtual quantity which is used to explain or investigate the flow conditions in a channel when you have non-uniform flow, mainly non-uniform flow. Of course, the critical conditions can be your normal depth as well. It is also possible. So flow may be critical depth may be equal to normal depth under uniform conditions. But in this case, yes, if the flow is the same, if Q is the same, and if you are considering a particular cross section for the channel, then critical depth is the same. That's why you see that this line is drawn with the equal depth. Okay.
Okay, sir. Thank you.
Right. So then can I stop now? Okay. Then thank you.